Okay, so in the last week we were working on discrete-time Fourier transforms. Move some light down to see things a little better. And you may or may not recall, so where were we? We derived the transform. We were looking at different ways to compute the transform of different functions. And we set the stage, and we're still working on the old notes. We set the stage by saying one of the really useful things to do with the discrete-time Fourier transform is to take the Fourier transform of the unit sample response and get this function HF that's the discrete-time frequency response of the system. And so if it's really useful, we want to look at a couple, how do we do this computation in a way that's as easy as possible. And our first method was, well, we can always rely on the definition. So if you give me any time sequence and I can apply the defining equation for the transform and compute a discrete-time Fourier transform for that. And we found, although that's usually not a good choice, for FIR filters it's actually not so bad. When we went through this example with a non-recursive and FIR filter that happened to be a two-point averaging filter, where the output was half the current input plus half the previous input. Finding the unit sample response was trivial. 1/2 delta spin plus 1/2 delta spin minus 1. We pick up the difference equation coefficients. That gives us the sample values of the mean sample response. Ran that through the defining equation of the transform. And we ended up with a little combination of exponentials that I showed you a little trick for how we could break that up into magnitude and phase easily by pulling out an exponential. And we ended up with a magnitude response in this system that looked like a cosine function. And a phase response that had a linear term versus frequency, and this either or term that had to do with whether the cosine was positive or negative. When that cosine was positive, we would add 0 phase to this. When it was negative, well, we would account for that by adding or subtracting 180 degrees or pi radians of phase. Now, some interesting things, and we derived all that, and we started looking at the implications of that. And one of them was that this linear relationship between the phase angle and the frequency is actually an interesting phenomenon. And today we're going to talk through that a little bit more, see what that means and where that comes from. And then we're going to derive another way, it's a simpler way, the more preferred way for doing discrete-time Fourier transform computations. And that will lead us to looking at some of the properties of the transform that we need to make that truly easy. And by the end, we'll get to the place where we're going to be able to take our favorite problem, convolution, and make it simpler by using discrete-time Fourier transform. So that's where we're heading. A lot of ground to cover in between here and there. We plotted the frequency response magnitude and phase of that averaging filter, and saw that the magnitude looked like this. Well, the cosine that you take the absolute value of, the phase has this linear phase response. And again, how we interpret that, we would look only at the principal range. And so from that viewpoint, we'd say, oh, we've got a low-pass filter, and I've got this very linear phase response. Well, okay, that's fine. What's so special about this linear phase response? Well, what's so special is you would love every system you design to have that kind of phase response, and you can't do it with any analog system, and a lot of discrete-time systems you can't get this either. You can only get this with certain kinds of discrete-time systems. That linear phase response, what punchline is, that relates to a time shift. Anytime I have a time shift on my time domain signal, we're going to see a linear response of phase versus frequency coming out of that time shift. And you can do that by assigning a time function that's a pure cosine that you pick the digital frequency you want. So it's a sample of a cosine signal. And then delay that signal by some number of samples, n delay. So this is just a fixed numeric value. If we replace n in the analytical argument with n minus n delay, and we simplify that by distributing through the 2 pi f0 everywhere, and we get the familiar cosine 2 pi f0 n, the changing part of the function that's a function of n, like it's supposed to be. And this term here is, well, 2 constant, pi is constant, n's constant, and, well, f depends on what frequency we're operating at, but we would call that the phase shift term in this, right? And that phase shift term is a function of the frequency of our cosine. And of course, if you plugged in all the values for pi and f and n, you would end up with radians like you're supposed to. So let's look at this function of frequency we have, 2 pi, and these 3 guys in blue here, or yellow, are constants. So this relationship between the phase that was created by delaying something in time by a time shift is a linear function of frequency. It's a constant slope. Right. That's why we say that time shifts invoke a linear phase response, a linear change in phase versus frequency, a straight line. So if I add a delay in time, I essentially add a linear phase term to whatever phase I had before. That would be a phase versus frequency with a constant slope. So something like this. Now, we should see exactly, if it's a pure time shift, we would see exactly a straight line phase versus frequency. Again, always be careful when you see jumps in the phase plot. Some of them are real, some of them are not. This is one that's not. I'm jumping from, well, this is minus pi to plus pi. This is just a wraparound of plotting artifact, because phase, when you hit minus 180 degrees, that's the same as plus 180 degrees. It's cyclic. So a 2 pi jump in phase is meaningless. A 1 pi jump is meaningful. 1 pi jumps come from terms like we had in that expression, where you have a magnitude, a function its magnitude is flipping signs, and that sign flip shows up as a plus or minus pi change in phase. So sometimes the phase discontinuity that comes from a SIGN sign change in the response. This one's fake. The slope of this function, though, is exactly this, minus 2 pi n delay. So the more I shift in time, the steeper the slope gets. That's all. Question?
So is n delay a value of time, like in terms of seconds?
Yes, it's a number of samples that you're delaying.
Okay.
So you shifted by 5 samples or 10 samples. So, but you can think of it as a time shift. Now, to connect why that kind of makes sense, that there's this linear relationship between phase and frequency, and my apologies to those of you who saw this at 228. If you take a 1 hertz sine wave, or cosine wave, and let's shift it in time by a quarter second. So I take it and I move it over by a quarter second. Now if I look at how much of a cycle of the original waveform did I advance, did I move it over, move the peak over by? Well, looks like I would have intersected the original function over here at about 1/4 of a cycle, or 90 degrees. So shifting by a quarter second was the same as advancing the phase of the sine of the cosine wave by pi over 2 radians, quarter second. If I shift a 2 hertz signal by exactly the same amount, that's same quarter second, and now say how much of a cycle did we advance on this 2 hertz cycle, 2 hertz square wave, or sine wave, sorry. Now we're going a half cycle, or pi radians. So the same time shift required twice, was equivalent to twice as much phase shift, if you will. If you've struggled with phase, always think of phase as fractions of a period. That's all it is. Right? So if I have a higher frequency, my periods are half as long. So the same time shift is twice as much phase. kind of makes sense. So there is naturally this linear relationship between frequency, time, and phase. Now, we have different measurements for the time delay that comes from phase. And you may or may not have seen this in continuous time systems. There were two different terms you can use, the phase delay or the group delay. These are both time measurements. They have units of seconds, but they're like how you turn the phase into an equivalent time shift. The phase delay is the time equivalent of whatever your phase angle is. You look at the angle of h at some particular frequency divided by 2 pi f to get the term time. And you get some unit of seconds that's purely translating the phase angle value into time. The group delay is also a seconds or time kind of measurement, but there you're looking at the slope of that phase curve, and turning that into an equivalent time shift. And so you still have minus 1 over 2 pi, but instead of taking the angle divided by f, you're taking the derivative, the slope of the angle versus frequency plot. In discrete time systems, we have equivalent kinds of terminology. We talk about the phase delay. Now these are in samples, not seconds, but it's the same kind of thing. We take the angle of h of f at some particular frequency, take the minus of it, and divide it by 2 pi times the frequency to get a phase delay. Or we take the slope of the phase versus frequency curve at a particular frequency divided by 2 pi and get what we call group delay, which is related to the slope. Now in most filters, most systems, these will give you two different answers. And here's an illustration. Here's an actual phase response of our simple IIR filter. Right on symmetry, it's all cool. If I said, what's the phase delay at some particular frequency f0, we'll find f0, find the phase plot, see what phase we have at that frequency, take minus that value, divide it by 2 pi times that frequency, and I'll have some number of samples, probably fractional ones, with what we would call the phase delay of our system. The group delay of that frequency, we take the slope at that same frequency point and divide it by minus 2 pi, and that would give us the group delay. It would also have units of samples, but it would be a different answer we would get out of that than we would get from the phase delay term. So typically, usually these are different, two different measurements of delay. Why do we like filters with linear phase response? Well, I claim they do not introduce any phase distortion in your signals. Meaning, no matter what frequency signal I put in, the system's going to uniformly delay them in time by a fixed amount. So if I put in maybe two different signals, or a signal that's a sum of two different frequencies, they're going to come out with the same time alignment after they go through my system. I'm not going to realign them at all. If I realign them, we would call that distorting their relative phases. I'm going to leave them. I'm going to impose the same time delay to this signal and this signal, so they come out with the same alignment. That means my system, my filter, if you will, is purely making them bigger or smaller, depending on what I wanted the filter to do. I'm not changing the relative phases. So that would be great. All frequencies experience the same time shift as they go through the linear phase system. What kind of filters can achieve that linear phase response? Well, I want it in everything I design, pretty much, unless I'm designing a system that's supposed to impose some phase shift like compensators for a control system. Usually I don't. Usually for filtering, I don't want them to be distorting the phase. Cannot make those with any analog filter. Most filters will have some region over which they have a linear phase response, but then it falls apart. Most IIR, well, all IIR filters also cannot have linear phase over the whole frequency range. The only ones that can achieve this are some, but not all FIR filters. IIRs cannot have completely linear phase. Again, they can have be linear in some region, but not over the whole frequency or span. And the key to a linear phase FIR filter is not only does its unit sample response have a finite length, which it has to be for an FIR filter, but it has to have sample values that are symmetrical around its center point. And it can have either odd or even symmetry. Either one works. So, busy chart. Sorry. So, for example, here's two different examples of an even symmetric unit sample response. We have some center value, and around that center value, we have the same values on both sides. Here's two examples of odd symmetric ones. Again, either side we have negative values. The difference between these two cases is whether I have a 1, 2, 3, 4, 5, 6, 7, an odd number of samples in my unit sample response that are non-zero, or an even number of samples. Same thing here. Odd length, odd symmetry, even length, even symmetry. And it turns out it actually matters which ones of those you have. All of these have the right symmetry to make a linear phase filter. So if I want to design a linear phase FIR filter, I could choose any of these combinations. Odd symmetry or even symmetry, odd number of samples or even number of samples. However, some of the symmetry rules of Fourier transforms dictate that some of these cases with certain symmetries that we have over here in the time domain impose other symmetries in the frequency domain that make it impossible to design certain kinds of filters. Like, for example, if I have a even length odd symmetric unit sample response, then the Fourier transform of that, the Discrete-Time Fourier transform, has to be odd symmetric around 0. And which means I have to go through 0 at DC. I can't make any low-pass filters out of that. And so you'll see over here a description of only certain kinds of filters can be made with certain combinations of symmetries and odd or even lengths of FIR unit sample responses. Okay, that's as much as we're going to say about it here. If you want to know more about this stuff, 419 is your thing. Digital signal processing, we learn how to design FIR filters. And as soon as we say we want a linear phase filter, we say, okay, I've got to do an FIR filter. And if I want to make my life easy, I'm only going to design this style, because I can make every single kind of filter with that, with the type 1, odd length, even symmetric unit sample response. And so that's usually how we design FIR filters, because those have less symmetry requirements imposed on them. And so we'll typically choose that style. All right? But again, the punchline of the story, I love linear phase. It's no phase distortion. It's a perfect filter. I can't make them with IIR filters. I can't make them with analog filters. I can only make them with discrete-time FIR filters with symmetric unit sample responses.
In terms of like the linearity of the phase response, I don't really understand how that makes it have no distortion, because it's like if you had like a quarter of the digital frequency plus like a half of the digital frequency, it's like at different points.
It's getting different phase shifts.
Yeah.
But those different phase shifts turn into the same time shift. So that's what we're preserving, the time alignment of our signals.
So it's like the right ratio of the frequency.
Right. So a difference is with we did with those sine waves, depending on what frequency you have, I need different amount of phase to get the same time shift.
Okay.
The higher the frequency, the more phase shift I need to get the same time shift.
Yeah. Cool.
That's so a linear phase response is no time shift. And the other interesting thing about FIR filters that are symmetric and linear phase is that the phase delay ends up being the same as the group delay. And that's because your phase plot is guaranteed to go through 0, and it's a straight line. So, dividing the slope value by f is the same as finding the slope, because it's a straight line. And it's a very predictable value. If the unit sample response has m samples, the group delay and the phase delay are m minus 1 over 2. Basically half the length of the unit sample response is the amount of time delay that your FIR system or FIR filter is going to impose on a signal going into it. So what are you thinking about that? The signal's got to get halfway into my filter before anything starts popping out. Okay. That was all an IIR filter, excuse me, FIR filter. That was a simple application of the defining expression for the discrete-time Fourier transform, which was what? So for that, we found h of f. We found that by doing a convolution, or not a convolution, sum from n equals minus infinity to plus infinity of h of n e to the minus j2 pi n capital F. So for our FIR filter, we plugged in the couple sample values, the couple non-zero sample values for h of n into this expression. We got a sum of exponentials, and we're off and rolling. For an IIR filter, recursive filter, not so easy. Here's one that we've been using as an example, and it's the simplest IIR filter, but so that we don't get lost in the numbers. And you can see the mechanics, we'll use this simple example, but it generalizes to other ones as well. We would have to find the unit sample response if we wanted to find the frequency response, and well, okay, you kind of know how to do that now. Infer it by recursion, by plugging things in the recursion table and say, that looks like an alpha to the n u of n. Or we could solve the difference equation for the unit sample response and say, aha, it's alpha to the n u of n. We'd have to go through something to find it. And yeah, we can get the characteristic equation and do all that stuff. All right. Okay. If I wanted to take that h of n and find its frequency response, I'd have to plug that analytical expression into this summation and then cross my fingers that I have a table somewhere that tells me what that sum is. It's probably some kind of geometric series, right? Some summation, and I'm going to need some help from some sum table somewhere like this. And hope it looks like one of these, sum from 1 to infinity of one of these, or these, or these. I've got to find something to help me out. Well, in that particular case happens to be one that there is a closed form solution for, so that's why we're using it as an example. We would plug alpha v and u of n in here, and this is what we did early on, the first day we were talking about discrete-time Fourier transforms. You make this alpha e to the minus j2 pi f raised to the n power. You've got a closed form solution for a sum from 0 to infinity of a to the n. So we would find that in the math book somewhere and say, there we go, aha, that's our frequency response, and cleverly break it up into magnitude and phase, and voila. Well, that's great if you have a simple function that there exists a closed form series summation for. If not, you're kind of out of luck. And so that's why we want to abandon the transform equation and get to use, I've got to use a lookup table anyway to get those summations. Why don't I just get the answer out of a lookup table? And so, just like in 228 for Fourier transforms, Laplace transforms, we're going to want to be able to just look up the transformations in a table, maybe adjust them based on some properties from this discrete-time Fourier transform, and do it that way. So, yes, indeed, there are tables. Your text has one, your textbook has one, which has our favorite flavors of signals and functions and time domain discrete-time signals and what their discrete-time Fourier transforms are, usually in F form. A lot of textbooks prefer this omega form. where capital omega is just 2 pi capital F. But either one, fine. And what we're going to talk about in more detail today, though, is, I mean, you can just look these up. I'm not going to drive any of them. There they are. But how we apply some of these different properties so that if I have a function that doesn't exactly look like one of these, but it's close, how we can modify these table lookup answers to accommodate other functions. Functions that have things like time shifts or time reversals or frequency shifts or anything like that in them. So that's what we're going to talk about. Just to show you the method is better. If we took our simple case here that we know we have an impulse response alpha and U of n, well, that is one that's right there in the table. We can just simply look up the answer and say, voila, there we go. There's my answer. But I don't have to do all that other mathematical gymnastics. And take that from there. We can break that up in magnitude if you want. And our FIR example, also trivially easy to use with table. We look up, well, delta suspends transforms a 1, so that becomes a half. And well, here I've got a shift by 1, so that's a case where I'm going to need some kind of property, a shift property. So we go look that up in the properties table and say time shifts. Okay, if I shift by that, then we'll apply my function by minus 2 pi mf, plug that in, and done. That's the way we want to approach it. Okay, before we do, we need to go over a couple of those properties. So, everybody okay with what we're doing, where we're going, why we're doing there? We're trying to make sure we've got a good set of easy ways to do discrete-time Fourier transforms. As I'm going to like them for finding frequency responses. And in 18 minutes, we're also going to see that they're going to let us do convolution as well. So let's get to this. Symmetries. We talked about this. Let's review. If you have a real-time function, you are guaranteed to have conjugate symmetry in your discrete-time Fourier transform, which means the transform value at a negative frequency is the same as the complex conjugate of the value of a positive frequency. What that means in terms of our magnitude and phase is that the magnitude response will be even symmetric around 0, 1/2, and all the multiples of those. And the phase response will be odd symmetric around 0, 1/2, and all the multiples. Funny things happen when we start imposing other symmetries to our time functions. If your time function x sub n is real, which most of them are, but now also even symmetric around n equals 0. It means it's probably not causal, but it's as long as it's even symmetric around n equals 0, then this is also true of its discrete-time Fourier transform. Its DTFT, that's usually a complex function, becomes a real function. It has even symmetry in the amplitude spectrum. The amplitude spectrum being if you just literally plotted h of f versus frequency, not its magnitude, but the function itself. That means its magnitude spectrum has to be even symmetric, obviously. If you plotted it as magnitude and phase, the phase would still be odd symmetric, which it has to be because this was real, but because the transform is real, there's no j's anywhere, so the only possible values for phase are 0, when that real number is positive, or plus or minus 180 degrees when it's negative. So there's only 2 possible values for the phase. For example, this is the discrete-time Fourier transform of a symmetric pulse around n equals 0. It's basically a repeating sinc function. If you just plotting x of f, not the magnitude, but just x of f versus f, it's even symmetric. It goes positive and negative. If you plotted this magnitude in phase, well, all the negatives would flip up on the magnitude. Notice a phase all has 0 values where this is positive, and either plus or minus 180 degrees when it flips negative. So the only phase values I'm allowed to have are 0 for positive values, plus or minus pi for negative values. That's if I started with a time function that was real valued and even symmetric around n equals 0. If you have a real function that happens to be odd symmetric around 0, this it would look like down here, down low, odd, and it has to go through 0. Odd symmetric around n equals 0. Its discrete-time Fourier transform is purely imaginary. And if you plotted it versus f, it would be odd symmetric. Now, the magnitude is still even symmetric, the phase is still odd symmetric, but the function itself is odd symmetric. And because it's purely imaginary, the only values I can have for phase are plus j, 90 degrees, or minus j, minus 90 degrees. So again, only two possible values for phase for a real valued odd symmetric function. All right, quickly, some other properties that carry over from some, just like the continuous time version. The discrete time Fourier transform is a linear operation, therefore superposition holds. If I add two time functions and take their discrete time Fourier transform, I add their transforms. If I scale them by scalar values, I scale their transforms. So that holds true. That's a statement of superposition, which all linear operations must obey. So I can add, if I add stuff in the time domain, I can just add up their transforms. I don't have to do anything else. If I scale them in one, I scale their transforms. If I take a time signal and reverse it, flip it around the n equals 0 axis, what does that do to its discrete time Fourier transform? Well, if x of n has a transform x of f, and I take that same function and time reverse it, I'll take this original transform x of f and replace f with minus f. The implication of that is if I had a real valued function, that this statement also is equivalent to saying you'll take the complex conjugate of that. Because the real signal is going to be conjugate symmetric. And how do we take a complex conjugate? Well, we make the imaginary part negative or the phase part negative. We'll put the sign on those two. Time shifting, well, it's what we've been looking at for linear phase. If you shift a sequence, either delay it or advance it by some amount, what happens to the transform? Well, if you delay it by m, you multiply it by e to the minus j 2 pi m times capital F, your digital frequency. Okay. Yeah, you can, I mean, in terms of what that does to your actual spectrum, if I multiply something by an exponential, that shift in time, again, if I multiply two complex functions, I'm going to multiply their magnitudes and add their phases. We know the magnitude of this exponential has to be 1, because it's a sine squared plus a cosine squared square root. So time shifts do nothing to the magnitude response. It's a pure phase response, and it's a linear phase response. Right? And it adds this slope to my phase term that has a slope of minus 2 pi m times f. That doesn't mean it replaces it with a straight line. It takes whatever slope function you had before. Let's draw a picture. With my angle of x of f was, I don't know, look like that. Now it's going to look like the same thing, but tipped up more. It's going to add some linear phase amount to it. So you can get tripped up though when you're working with causal signals. So let's take a couple examples here just to show you how the time shift property can work. and what dangers you can run into. So we know if you take the discrete time Fourier transform of 1/2 to the n u of n, we've already derived many times. That's 1 minus 1/2 u minus j 2 pi f. 2 pi f. Okay. If instead of that I said, well, what's the discrete time Fourier transform of 1/2 the n plus 3? Keep my notation straight here. U of n plus 3. And here I'm changing both indices, so this is a truly a time advance. My starting point moved by 3, as did my function. And according to this property, I'll take my original answer, minus 1/2 e to the minus j 2 pi f, and then scale it by what? I have a time advance, so that's e to the plus j 2 pi, and I'm going to need the amount that I shifted it and my frequency variable f. So that's purely applying the time shift property. Where you can get in trouble is a case like this. Here's a 1/2 to the n minus 2 u of n. That's not a pure time shift. Well, at least it's not a pure time shift of this function. So I can't simply use the property for this one if I want to know what's the discrete time Fourier transform of that. Any ideas what I might do on this one? Yeah.
The -2 could be turned into, you could do like 1/2 times to the power of -2 times 1/2 to the power of n.
So take a minus 1/2, or 1/2 to the minus 1/2, multiply by 1/2 to the n u of n. This I know the transform of, and what's that? That's just constant. That's just 4. So that becomes simply 4 over 1 minus 1/2 e to the minus j 2 pi f. So be careful if you're, before you apply time shift, you need to make sure you can. Yeah.
What if the unit step was being shifted rather than the function? Like it was u of n minus 2.
Let's do it over here. So if you had a like a 1/2 to the n and u of n, I don't know, plus 1.
Yeah.
I'm going to transform that. I do the same thing. I want to get the arguments the same. I'd say that's 1/2 to the minus 1 times 1/2 to the n plus 1, u of n plus 1. Apply the time shift to that and multiply it by 2.
Wait, where did you get, what just happened?
Magic just happened. Would you agree that this is the same as that?
Oh,
Yes.
yeah. Okay.
So that's a 2. Right. So I still need a time shift. I haven't had my 1 over 1 minus e to the 1/2 e to the minus j 2 pi f. That 2 would give me a 2 out in front, and I still need the exponential term shifted by 1 e to the plus j 2 pi f out there. Yeah.
In general, do you want to represent the exponent of the function as an argument of
Do I want to say that again?
do you want the exponent to match the inside of the section? In general, like, is that how you-
Yeah, usually you've got to match the u of n. If you're looking at to use a transform of a causal signal that has a u of n in it, you've probably got to match up the u of n transform. You could have also said, well, this is the same thing as a shifted version, something times u of n minus 2 plus the n minus, or the n equals 1 value plus the n equals 0 value, and then you have some really messy mathematics, but easier this way. Other questions? Yeah.
So the original 1/2 to n u of n, that's just like a known Fourier transform?
Yep.
Okay.
Right, so this is, again, the idea is here, you've got a table of known transforms. If you've got something that's close, you'd like to be able to use that transform, but you may need one of these properties to tell you how to modify things. That's exactly what we're looking for. Okay. Real quickly, get us to our major punchline for the day. There's a rule to the time shift property, that's the frequency shift property of inverse transforms. It says, if x of f is my frequency, my discrete-time Fourier transform, and I find its inverse transform is some time function x of n, we ask the question, if I shift this transform by f0, so shift in frequency, what did I do to the time function? And the property is, just like time shifts cause me to multiply spectrum by e to the j 2 pi f's, 2 pi n f's, a frequency shift means I've got to multiply the time function by e to the plus j 2 pi n f, where f0 is the amount that I shifted the transform. Now, x of n here was probably a real function. If I shift its spectrum, I no longer have a real function. I've got a complex time function now. That's not so good. So you got either plus j to the minus, yeah, nasty. You can avoid that by doing a combination of shifts. By shifting 2 copies of the frequency spectrum, one at plus f0, one at minus f0. So if you've got some known frequency response for transform, and the property tells you what to do if I shift that whole thing over by f0, multiply the exponential times the time function. If I do the same thing but shift it down by f0, same function. If I do both, I add them together, I take my time function, I multiply it by the sum of 2 conjugate exponentials, which is a cosine. So that's the discrete time version of AM radio, even though there is no such thing. It says, well, turn it around, it's the frequency modulation property. If you take a time function, multiply it by a discrete cosine, you take its spectrum and shift it 1/2 to at plus f0, 1/2 to minus f0. So take any time function with a known Fourier, discrete time Fourier transform, that's not actually the right one, this one, but just for the picture. We multiply it by a cosine, which has a spectrum of a couple of impulses here, in continuous time systems anyway. We get some product in the time domain, but what happens in the frequency domain is I make a copy of this at f0, make a copy of this at minus f0, one at plus f0, each with half the amplitude of the original. Okay. So that's what happens when we multiply things by cosines in the time domain. Now, in 1 minute or less, that's not so useful. Well, it's useful if you start multiplying things by cosines. More useful is the dual of this. What happened when I multiplied these 2 time functions? What happened to the spectra? What operation did I do to them? Involved them, just like it was in continuous time systems. So we have 2 important properties. The multiplication property that says if I multiply 2 time functions, I convolve their spectra. Except it's a new kind of convolution. It's circular convolution. Because I'm convolving now 2 periodic functions, right? Spectrums are periodic now. And so I get a repeating answer. I get a circular convolution. More importantly, the punchline is the dual. To convolve things in the time domain, it's multiplication in the discrete time Fourier transform domain. That's the one we do. That's what we like. Because we don't like convolving stuff anymore. We like multiplying stuff. So, if you want to do system analysis, if you want to find the output for a given input, you take, instead of doing convolution, we'll take the problem into the transform domain and say, instead of convolving those time functions, I'm going to multiply their Fourier transforms, the discrete-time Fourier transforms. Which means multiplying the magnitudes, adding the phases. That's how we're going to do system analysis from now on. There's punchline. No more convolution. Yay. All right. See you on Friday. Stay cool till then. And we'll start actually doing some system analysis using the transforms.
How did that last part, I got how the convolution, or the multiple